Okay, welcome everybody to the class. I hope you can hear me now. Okay, welcome everybody to the class. So we've moved to another topic and the topic is curve fitting. And basically, when you are given a set of data, we want to be able to fit a curve around the data to be able to want to develop a model given by the data, and the model is just a curve that's going to explain the variations we have in the data. So basically what this topic is all about is that when you are given a set of data points, you can fit a curve around the data in order to describe the general trend of the data. That's how the dependent variable changes as a function of the independent variable. And there are different methods that can be used for curve fitting. But the method we are going to consider in this course is going to be least-squares regression. So the methods of least-squares regression that will be considered are the linear regression. So for linear regression, we are going to fit a straight line and through the data. So trying to describe the general trend of the data using a linear or a straight line. But for polynomial, we're going to use like it becomes a curve when it becomes because this is just first order. Linear is just first order polynomial, but when it becomes polynomial, it's like greater than or equal to 2. So this is what we're going to be considering in this class for today. So if we have some sets of data points, x and y, and reaching up to n, in order to fit a straight line, a linear line through the data, we are going to make use of this equation. So y is equal to mc. So this is a straight line. This is a straight line curve. So I'm sure you must have encountered this equation. So this m is the slope of the line. This is just a straight line curve where m is the slope of the line. Then c is the intercept on the y-axis. So this, for linear regression, we are fitting this straight line through the data, but we introduce another variable called e, where e is the error, because we are fitting a set of data points, and it's not likely that we fit it perfectly. So we just introduce this e term, the error term, to describe the error or the residual that that remains to account for the error when fitting this straight line into your set of data points. So the error, making the error the subject of formula, you're going to arrive at this equation. So the general objective, the objective is to minimize the error, is to drive the error to 0, because once the error is 0, you know that you have a perfect fit of your data points, and the line you are trying to fit passes through all your data points perfectly. So that's, we want to drive the error to 0. And there are different methods that can be used But the method, the best method is you want to minimize the error, but the best strategy is to minimize the sum of the squared errors. So you are minimizing the sum of the squared errors where this error is given by this formula. So the error squared is just simply this formula squared. Then you want to minimize the difference between the measured, the data points you are given and your model, where your model is given by, this is your model, y is equal to mx plus c, and the measured point is the y point in the data. So the best method, there are different methods. If you look at the textbook, they consider different methods. One is just to minimize the error, but it has its own limitation. But the best method is to minimize the sum of the squared error, which is given by this, because the error is given by y minus mc minus c, which is this equation. So if we can minimize this error, we are driving the error to 0. So we represent this as s subscript r. So if this s subscript r is equal to 0, then we know that our line, the line we are trying to fit into the data, through the data point, is the best fit. That curve is the best fit for the line. So what we are trying to do is we are trying to minimize this SR. So this is the best um, way to minimize the error and to fit a perfect line given your data point. And we are going to be working with this particular equation. So we want to derive an equation whereby we get our m, because this is y is equal to mc. This is the straight line we want to fit. So we want to derive a formula for m and want to derive a formula for c. In order to do that, we are going to differentiate this particular equation with respect to each of the coefficients. So we differentiate this with respect to c, c being the intercept. And when you differentiate it, you arrive at this equation. Then you're going to differentiate this same equation now with respect to n. So the SR, the m. This is the result of the differentiation. So in order to minimize SR, remember that we want to drive this to 0. In order to minimize it, we are going to set the derivative to 0. So the next set of equation, we set this equation and this equation to 0. Then we expanded out this term and we expanded out this term. But since this is going to be equal to 0, the minus 2 is going to cancel out, because you can just divide both sides by minus 2. Then, because here is 0, if you divide both sides by minus 2, it's still going to give you 0. So you have only this, then you expand it out. We're going to arrive at this equation. Then this is a summation sign. So you are summing from 0 to n, because you are summing over a constant. So this summation sign here is just equal to n multiplied by c, because you are summing from 0 to n. And since it's a constant, you are summing over. So this summation is equal to n times c. So just replacing this with this particular summation with n times c and making this the subject of formula here, you arrive at this equation. Then making this one the subject of formula, you arrive at this equation. So we've reduced the problem into two sets of linear equations. I want to get the slope m and want to get the intercept c. In the last class, we considered solving algebraic equations. So you can use, there are two simultaneous equations. So you can use elimination method or any of the methods we used previously, and I skip that step. So if you do that and you make, then we are solving for M and we are solving for C. So when you solve for M, you arrive at this equation. You can try to do it on your own to prove that this is indeed the solution. Then we'll make C the subject of formula using equation 4. So if you make C the subject of formula, you just divide all the coefficients by n, then you arrive at this equation. But the summation of y over n, like you are summing the value of y over the entire number of sets, which is n. So that's the mean, the y mean. Then this is the average of the x values. So this equation equals to this equation. So we've been able to, this is just derivation I'm just explaining. So we have been able to find the slope of the line, giving you sets of data points. And you can find, using this formula, we use it to find the intercepts, giving the sets of data points. So what we are trying to do is that we want to fit, if you are given a set of data points or a set or a data, we want to be able to fit in a straight line through the data. And what I've just done is and the straight line is given by y is equal to mc. So what I've just done is to prove how to get your m, which is your slope, then how to get your c, which is your intercept. We are going to use an example to explain it. So we are saying that fit a straight line to the x and y values in this, given this data set. The, what we are going to do is just to use this equation. Let me just bring it out here. So we want to use this equation to get m and want to get c. So what we need is to want to get m. This is our m. This is our m. Then in order to get m, we need the summation. Okay, these values, x and y values, were given in the question. So we need to sum all of this because we need the summation of x. So this is the x column. So in the equation, we need summation of x. So we need to sum all of this, and the summation is 28. We also need the summation over the y values. So these are the y values. So if we sum all of these, we'll get 24. Another thing we need is the summation of x squared. So we are going to square all of these. So the square of this is equal to this. Then we sum all of this together, and the summation is equal to this. So we need this. That's why we summed all of this together. Then we need this summation. We'll multiply x by y. Then we sum all the elements in the cell together. So you multiply x by y to get this. Multiply 2 by 2.5 to get 5. And after that, you will sum all of this together in order to get this. So we already have all the values we need. Then to get the C is the intercept. So for the intercept, this is the formula we are using. So to get C, and this is the formula we are using. So we need the summation of y, and the summation of y, we already have it. Then we need n. In this question, n is the number of of data points you have. So 1, 2, 3, 4, 5, 6, and 7. So n is equal to 7. So we already know all these values from the table and the summation. So you just put in all the values to get your m, then your c. We already know these values, which we calculated. This is 24. Then this is 28 divided by 7. So when we just do that, we arrive at the intercept, which is given by c. So therefore, the straight line, the least squares fit, is given by these values. So m, because mx plus c. So we got the value of m as 0.8. Then our value of c was 0.07. So this is the line that provides a best fit for the data. So after getting this particular equation, we need to plot the line. We need to plot that particular line. So to plot the line, we are going to make use of this equation here. And in place of x, so we are going to plot this line. So in place of x, we are going to use this value of x. So for x1, so I just want to tell you how to plot the line. That is straightforward. So for x1, you just put the value x1 was 1 in the question. So it's 1. So you put in this straight line, you arrived at 1. So for x2, you put in 2. So given the line we derived, and so you continue until you get to 7. So this is the line that we came up with that best fits the data points. Then these dots, these data points are the actual sets of data. So you have your x and your y. So these values are these blue data points. So they are the blue data points, while this line here is the line that we calculated that best fits, that we derived, that best fits the data point. So we need some quantification in order to be sure that this line actually provides the best fit for the data. So like I said, this was the table I'm looking for. So these are mx1, mx plus c. The mx plus c is actually this one we derived. So here is this is the equation we derived, and it's just x. So in place of, for this value, you just put in x here. For this one, you put in x when x is equal to 2. For this point where x is equal to 3, then we arrive at this column. So this line is the plot of this line, of this and this, gives us the straight line curve, the red curve we derived. Then the plots of this and this gives us the blue data points we arrived at. So we need to actually quantify maybe the line we derived, if it's actually the best line or not. In order to do that, we need to estimate this value. So y minus mx minus x. So this is minus c. Minus c. So this particular equation is the error. So is the sum of the squared error, because this equation is the one we expressed here. Is the one we expressed here. I know we are trying to minimize this particular value because this is the error. So the error is the difference between the data points we're given and the model we derived. So we want to know the error. I want to drive this error, this particular highlighted equation, we want to drive it to 0. So we need to also include it in the table. So that's why I have it here. And there is a summation, is the sum squared of the error. So basically what we are trying to do is that this is the values we were giving. These are the measured values, and this is the model we have. This is the model we derived. That is the line that best fits the data point. Then this is like the error. So here is just we are subtracting this from this to get this. You're subtracting this. So y minus this to get this. And we want to, and we're going to sum all through the error. We're going to sum over the error. And when we summed over the error, we arrived at 2.99. Remember that we are trying to drive, this is the error. We are trying to drive it to 0. And we got like, the value is like approximately 3. So we're a bit sure that the model we derived is actually a good fit to the data. If you had gotten a very large value of this, maybe we've gotten 20, we know that you're going to know that this the line you got is not really a very good fit, because we want to drive this to 0. So this is like we did our best and we arrived at approximately 3. So we are a bit good. So the first thing is that after you derive your model to fit the data, you just visually inspect the line compared to the data points you are giving. And visually inspecting it, we can see that, okay, yes, it's actually a good fit to the data. Then after that, you are going to measure your error, because initially we want to drive this error to 0. So if it's very, very close to 0, then you know that you are in the right direction. Then another way you can quantify if what you've done is actually the best line, if the line you fit is actually the best line, is to measure the standard error of the estimate. So, and the standard error of the estimate is given by this formula, where SR, this SR is this SR we have here, is this error we have here that we want to drive to 0. So this is the SR. This is where the SR came from. And in this particular question, this is the SR. So in order to measure, in order to quantify what we have done is actually very good or not, you're going to measure this value, which is the standard error of the estimate. And using this particular equation, and you are going to be seeing um, how this value helps us to really quantify what we've done. But another measure we can use is called the correlation coefficient. So the correlation coefficient is called R, and is given by this formula, while R squared is called the coefficient of determination. So in order to quantify if what we've done is actually good or not, we want to this correlation coefficient, it has to be very close to 1, or it has to be equal to 1. If it's equal to 1, then we know that that line is like a perfect fit. The line passes through all the data points and we have a good line. And if it's 0, that's if it's very, very far from 1, that means that the line is not so good. The line that we fit through the data is not so good. Then also we want to make this SR to be equal to 0. So in the next question, we are asked to compute the measures that we can use to quantify the model that we fitted into the first question in example 1. So we have to calculate the standard deviation. So the standard deviation is given by this, where this is the sum squared of the measured y minus the mean, the y mean. So this is a standard deviation. So we need this particular equation. So yi minus y. So that was why in the table I included yi minus y then squared. So so this is the y high, then minus the mean. So the mean is just 24 divided by 7. Then you have this table, then you will sum it together. So that's why I had this column in the table, because we can use it to calculate the standard deviation. So putting in the values, we got 1.945. Then the standard error of the estimate. So the standard error of the estimate is given by this equation, where this SR is the error. So this SR came from here, is this particular value. So we are trying to minimize this. We are trying to drive this to 0. So it's 2.991. And that's how, so this is 2.991. Then N is the number of data points, which is 7 minus 2. So we got the standard error of estimate. Now, the correlation coefficient. So the correlation coefficient is simply given by this formula, where this one is the standard deviation, then this is the error, is the sum squared of the error, and this is the standard deviation. We arrived at this. So the the correlation coefficient is given by this. Then ordinarily, I said that we want to make these values to be equal to. The ideal case is that if this correlation coefficient is equal to 1, then we know that we have a perfect fit. So it's kind of close to 1. So we know that what we've done is actually very good. Then the R squared, it's kind of accounts for the variability in the data point. So if we are trying to attain 100%. So if we have 100%, we know that there is 100% variability in the data set, and that it's 100% accounts for the original uncertainty that has been explained by the model. So we are a bit close to 100%. So we know that the line that we fitted is actually a very good fit. So I want to go to another example. So this example is that, so this example is saying that you are given, so we actually encountered this particular model. This is the model of the falling objects. We actually derived this in the first class, in the very first class of this course. So we derived the velocity of a falling object given by this. So this is a mathematical model. So if, for instance, you have another model, suppose like another person derived another model, and this was the model, is an empirical model, is given by this, and you have your measured points. So this is the question, right? So the velocity of a falling object was measured with time. So at t equal to this particular time steps, this was what was measured. Like, this was the measured data. Then this one is based on the model we derived. on this mathematical model, this particular mathematical model, giving these values. So all I did was just to put in these values, these particular values into this model. Then I did to produce this particular column. But this one is actually given in the question. So I produced this based on the mathematical model we derived previously. Then this one is just another model, is an empirical model of the velocity of a falling object, and is an alternative to the mathematical model, even though we did not derive it. So this is the equation. Then I simply put in the values of M 68.1, G 9.8, then C 12.5, then at different time steps. So at t is equal to 1, at t is equal to 2, you have this. At 3 is equal to 3, you have this. So the question actually says that we should determine which one is the best model that explains the velocity of a falling object. You know that this is the measured, this is what, this column is the measured values. So an experiment was actually conducted. Then the velocity of the ball at time t is equal to 1 is given by this. Then at time t is equal to 15 is given by this. So this is like the correct measurement. So this is the correct data. But we have a model, and we derived the model. So based on our model, this was the value, or these are the values we got based on the model. Then there's another model, empirical model, and these are the values we got based on that empirical model. And we are asked to, so this particular question is trying to say that which is the best model that describes the velocity of a falling ball. So these are the actual values, but our model, when we derived the model, we got these values. Then probably another person developed another model, and based on the model the person developed, he got this. So the question is saying that we should use the principle that we've just learned, the principle of curve fitting, in order to determine which is the best model in order to calculate the velocity of a falling object. If this is actually the best one, or this is actually the best one. So as you would have guessed, what we are going to do is that we are going to use those values. We are going to fit a straight line through these values. Then after that, we are going to construct another graph. Then we are going to fit a straight line through these values, the one I highlighted. So we are going to fit a straight line through this and this. Then after that, we are going to fit a straight line through this and this. Then we are going to use the quantification, all those parameters I talked about, like the standard error of the estimate. We'll use the correlation coefficient if is equal to 1 to really see which is the best model for the velocity of a falling object. If it's the one we derived previously, or is this one that somebody is presenting to us and telling us that this is the model for the velocity of a falling object. So want to be sure if it's which is better, either this or this. So we are going to use curve fitting. And like I said, we are going to fit, we'll construct this point, then we'll fit a line through it. Then after that, we'll construct this particular graph. Then we are going to fit a straight line through it. Then we'll compare the correlation coefficients, the standard error of the estimate, the slope, the intercept. So apart from the correlation coefficients and the standard error of estimates we can use, is that if this particular model, we want to determine which one is best. So if this particular model is like the best, if this one is the best model for the velocity of a falling object, that means that the slope we arrive at is going to be equal to 1 and the intercept is going to be equal to 0, because that it just means that this one and this one, they are the same thing exactly. And it also applies to this. That's when we construct, when we get the intercept and the slope of the line. And also the one that has the correlation coefficient close to 1 is actually the best one. The one that is closest to 1 is actually the best model for the velocity of a falling object. So that's what we want to do in this question. And in order to do that, we need to find the slope of the line. I remember the slope is given by this particular equation. So we need so this is the equation. So this is our x and this is our y. This is the first y and this is the second y, because we want to compare these two together. So we need the sum. So this is our x. So the summation of all of this is given by this. The summation of this one is given by the bolded number. Then the summation, this is our second y, is given by this. Then remember, in the formula, you need to calculate the summation of x multiplied by y. So that's why we summed, we multiplied, this is the x and this is the y. So this is it here. Then you need to sum it and getting these values. Then we need to calculate x squared, because we need to sum over the x squared because of this, the summation over x squared. So that's why we have this particular column. Then for this second, this is for the first model. So this is for the first model. Is the first model that we derived in the model 1. Let me just call it model 1. Then this is model 2. So this is the model somebody is presenting to us and saying that, okay, this is the model of a falling ball or a falling object, and we want to really determine which one is the best. So this is for the model 2. So I'm going to end the meeting